Hey everyone, and welcome back to the podcast. I'm Mark, and I'm really buzzing about today's topic, seriously excited.
And I'm Jenny, ready to try and keep Mark grounded as he gets super enthusiastic about something new and potentially world-changing. What have you dug up this week, Mark?
Okay, so you know how everyone's talking about quantum computing, the qubits, the super cold temperatures, the potential? Well, imagine a computing paradigm that could possibly solve similar complex problems, but without needing near absolute zero. And it might be very energy efficient. Talking about probabilistic computing.
Probabilistic computing. Okay, so it's not quantum, but it's also not like my laptop. Let me get this straight. It uses probability. Somehow?
Exactly. Instead of classical bits that are a definite 0 or 1, or qubits that are a superposition of both, probabilistic computing uses p-bits. Think of them as bits that are constantly fluctuating between 0 and 1. It's harnessing that inherent randomness, that thermal fluctuation, which traditional computers fight against.
So instead of fighting the noise, it's using the noise? That's counterintuitive. How does that help compute?
That's the beauty of it. By allowing these p-bits to fluctuate, they can naturally settle into states that represent solutions to complex optimization problems. Purdue University and Tohoku University did some foundational work on this back in 2019, showing how these systems could solve specific problems more efficiently than classical methods, and maybe even more efficiently than quantum for certain tasks.
Okay, efficiency is key. I heard something buzzing around about incredible energy savings, like millions of times more efficient than a GPU. That sounds almost too good to be true.
Right? It does. The claims out there are pretty bold. Research from UCSB, specifically from Dr. Karam Kamsari's group, has shown significant energy efficiency improvements. They have a prototype built on an FPGA, a field programmable gate array, which is basically reprogrammable hardware. This prototype demonstrated sampling rates that exceed current quantum computing implementations by leveraging intrinsic CMOS variability. Basically, the natural fluctuations in the silicon chips are being used productively.
An FPGA? So we're not talking about building entirely new data centers with super refrigerators? It could potentially run on existing tech?
That's a big part of the appeal here. The potential for commercialization using existing FPGA hardware is a significant advantage. It means the barrier to entry and the cost infrastructure could be much lower compared to traditional quantum computing, which, let's be honest, requires a massive investment in entirely new hardware and environments.
That makes a lot of sense. So if it uses p-bits, and it's energy efficient, what kind of problems is it actually good at solving?
The sweet spot right now seems to be complex optimization problems. Think about things like finding the best route for a delivery network, optimizing financial portfolios, or even designing new materials. Purdue actually demonstrated solving a factorization problem using p-computers, which is a classic benchmark problem in computing 4. UCSB's FPGA implementation has shown significant speed improvements for these types of tasks.
Optimization problems. That covers a lot of ground in various industries. The research mentions performance improvements up to 6 orders of magnitude better than classical methods for certain problems. 3? That's a massive leap.
It is. And it's not just about speed, it's also about energy. The energy per operation can be at the femtowatt level, which is dramatically lower than the milliwatt level of classical computing. This is partly due to what's called thermodynamic computing, where you're using thermal fluctuations in a controlled way. It really minimizes data movement, which is a huge power drain in traditional systems.
Okay, so energy efficiency, potential for using existing hardware, and tackling optimization problems. Where does this leave quantum computing in the picture?
That's a great question, and it's something the researchers are open about. While quantum computing holds immense promise for specific problems like breaking modern encryption with Shor's algorithm, achieving fault-tolerant quantum computers with millions of qubits operating reliably is still a ways off. Probabilistic computing, on the other hand, seems to offer more near-term, practical advantages for a different set of problems, particularly optimization and sampling tasks.
So it's not necessarily a replacement for quantum, but maybe a complementary technology? Or even a bridge tech?
That's how some see it. It offers solutions that are needed right now for hard problems, leveraging technology we understand better and can build upon with existing infrastructure like CMOS and FPGAs. The scalability seems more direct, growing approximately linearly with complexity, unlike the exponential limitations classical computers hit for certain problems.
And the experts agree? We saw Dr. Karam Kamsari mentioned from UCSB and Professor Supriyo Datta from Purdue. What are they saying about the bigger picture?
Dr. Kamsari highlights the sampling rates achieved, pushing beyond current QC implementations by using intrinsic CMOS. Professor Datta points to the potential for solving problems like factorization with far fewer qubit count projections than needed for Shor's algorithm. They're seeing this not just as a theoretical curiosity, but as something that can solve real problems with demonstrable efficiency gains right now.
It brings up an interesting point about resource allocation, too. The research suggests probabilistic computing might require under $50 million in R&D, compared to potentially over $10 billion for a full quantum ecosystem. That's a substantial difference in investment.
It is. And that raises the question, should governments and companies prioritize funding PC development for those near-term gains and lower infrastructure needs, or continue the significant investment in QC with its promise of future breakthroughs? It's a substantial debate point.
A fascinating debate. So, what's next for probabilistic computing? Scaling up?
Definitely scaling. The goal is to scale up to millions of p-bits. 4. There are also efforts to make the nanodevices that generate the randomness for the p-bits faster and more energy efficient themselves. We're looking at developing more sophisticated software frameworks to program these probabilistic systems effectively as well.
It sounds like a really exciting area to watch. From harnessing noise for computation to potentially providing a more accessible path to solving complex problems, it's quite a paradigm shift.
It genuinely is. It's a reminder that there isn't just one path to the future of computing. Probabilistic computing is carving out its own niche, offering significant advantages, particularly in energy efficiency and cost, for specific, important problems. Keep an eye on this space. It's moving fast.
Okay, I think we've covered a lot here. Let's maybe think about some of the listener questions this might bring up, like how does this actually feel in practice? If I'm using a service powered by probabilistic computing, would I even know?
That's a good point. For the end user, you probably wouldn't interact directly with the p-bits or the hardware. It would be more about the results. Imagine using a mapping app that gives you a more efficient route in real time, even with sudden traffic changes, or a financial service that optimizes your investment portfolio more effectively based on market fluctuations. The gains would be in performance, speed, or potentially lower costs passed on to the user because the system is more efficient to run.
So the benefit is more on the infrastructure and behind-the-scenes side for now.
Precisely. It's optimizing the complex calculations that make those user experiences possible. Another potential area is in AI and machine learning, particularly for sampling problems that are currently very computationally intensive. Probabilistic computers could potentially speed up training times or enable more complex models.
AI. Of course, everything seems to tie back to AI these days. So in the short term, we're looking at optimization for things like logistics, finance, and perhaps some niche AI tasks. What are some of the hurdles they still need to overcome?
Well, one is that scalability challenge we touched on. While it shows potential for linear scaling, achieving that with millions of reliable p-bits and ensuring their interactions are precisely controlled is a non-trivial engineering task. Another is the software side, developing robust and user-friendly programming models and libraries for these types of systems. It's a different way of thinking about computation.
Yeah, I can imagine. Moving from deterministic classical computing to something inherently probabilistic requires a different mindset for developers. Are there any companies actively working on bringing this to market?
Yes, there are. While still a relatively young field compared to quantum, companies are starting to explore commercial applications, often spun out of university research. They're focusing on building those FPGA-based prototypes into more robust systems and developing the software stack. It's certainly an area attracting attention.
It feels like we're at the early stages of something that could have a substantial impact, even if it's not the quantum leap everyone talks about.
That's a fair assessment. It might not be the answer to every computational problem, but for a specific class of complex tasks where energy efficiency and cost are major factors, probabilistic computing seems to be offering some very compelling solutions right now. It's a good reminder that innovation can come from unexpected places, like embracing the randomness instead of fighting it.
It's definitely given me a lot to think about. It's not just about how fast we can compute, but how we can compute smarter and more efficiently.
Exactly. And that efficiency has broad implications, from reducing the environmental impact of data centers to enabling new applications that were previously too computationally expensive. It's a space to watch, no doubt.
We definitely will. Thanks for breaking down this complex topic, Mark. It's certainly given me a lot to consider.
My pleasure, Jenny. Always fun digging into the future of tech. And thanks to all of you for listening. We'll catch you on the next episode.
Bye, everyone.